Hello, everyone. We're going to talk about the second week of lab number 11, analysis of an unknown acid. So the whole goal of this experiment is twofold. We want to determine the concentration of an unknown acid using titrations. We also want to determine the identity of the unknown acid, what the unknown acid actually is. The way we're going to address both of these problems is by measuring a titration curve for a reaction between sodium hydroxide and this unknown acid. So we're actually going to be measuring a titration curve and using these titration curves to figure out both the concentration and the identity of the unknown acid. So let's talk about how we're going to do this. So the first part, determining the concentration of the unknown acid, is essentially what we did in week 1 of this experiment. We can use the idea of at the equivalence point of this reaction, at the equivalence point of this titration, the moles of the unknown acid are the same as the moles of our sodium hydroxide. Well, if we can then figure out the moles of our acid, how would we find the concentration? The concentration of the acid is simply the moles of the acid divided by the volume of the acid used. Okay, how do we determine the identity? This is a little more complicated, so let's go ahead and talk about it. All right, so the whole point of week number 1 was to standardize our NaOH. What do we mean by standardize our NaOH? The whole goal of week 1 was to accurately determine the concentration of our sodium hydroxide. Now that we know the concentration of our sodium hydroxide, we can use this in a titration, a lot like we did in week 1, to figure something out about our analyte down here. So this week we're going to do this in a beaker. Again, we have our sodium hydroxide in our burette. Down here, we have 25 milliliters of some weak acid, HA, that we don't know what it is. We're trying to figure that out. Okay, so we accurately know the concentration of our NaOH up here. We're going to slowly add NaOH to our analyte, to our HA. And what we're going to do is measure the pH as this reaction proceeds. And the whole goal is to construct a titration curve. So this titration curve, which you're going to use the data that Scott gives you that he measured in the lab. Actually, I'll just consolidate that data and post the Microsoft Excel spreadsheet. And you're going to make these titration curves on Excel. So for each of our 2 runs, there are 2 trials in this experiment, you're going to make a plot of pH on your y-axis versus the volume of NaOH added. So milliliters of NaOH added. Okay. I'm going to move this over a little bit. pH versus volume of titrant added. Okay. So what happens? Let's relate this to your lecture and what you're doing in lecture involving titrations. Remember, the pH meter is always down here. We're always measuring the pH of this solution. Okay. So we have to think about what's floating around in this solution and what the pH of this solution is going to be. All right, so what would the y-intercept be? That would be the pH before any of our base is added. Well, before any of our base is added, what's the pH? It's just some amount of a weak acid. In lecture, you could calculate what that pH would be if you knew what the weak acid was. What we're simply going to do in this lab is measure the pH. But suffice it to say, it's an acid, so the pH should be below 7. Should be low. And as we add NaOH to this, as we open this stopcock and let NaOH go in, the pH better be going up because we're adding a strong base. And the pH goes up as we add NaOH the whole way through this reaction. But exactly how the pH changes is important to understand. Okay, so as we start adding our NaOH, the pH starts going up, and everyone can agree with that. But we have to think about how this pH is going to change. Well, it depends on the reaction taking place. So let's go ahead and let's write a balanced chemical equation for this reaction taking place. So we have HA, we're adding our strong base, which again, the important thing we're adding is OH minus. This reaction goes 100% to completion to make what? To make water and A minus. Wish I had a bigger board. It's okay. That is my balanced chemical equation. Our HA reacts with OH minus, goes 100% to completion to make water and A minus. All right, so before we add any NaOH, we just have HA, it's acidic. As we add our NaOH, this reaction happens. We got to think about what happens to the pH. Okay, what does the equivalence point mean? At the equivalence point. What that means, remember from last week, is these reactants are in their stoichiometric ratio, meaning the moles of HA equal the moles of OH minus. Okay, well, if we add equal amounts of HA and OH minus, both of them are completely used up. So the only thing we have at the equivalence point is products. Well, what are our products in this case? We have water and we have A minus. What's A minus? HA is a weak acid, A minus is a weak base. So what's going to be the pH at the equivalence point? Is it going to be 7? No, the pH should be above 7 because all we're left with are products. And in this case, A minus is a base. Okay. What about before the equivalence point? Well, let me remind you guys, this is a limiting reactant problem. Okay, this reaction goes 100% to completion. So if we want to know what we're left with before the equivalence point, we have to think about what we have in this reaction. So I'm just going to erase this for a minute. Let's talk about before the equivalence point. How do we find the pH of a solution before the equivalence point? Well, it's a limiting reactant problem, and we need to set one of these BCA charts up. So hopefully you've been doing this in lecture, you've seen this in lecture. This is not an ice diagram. It looks like one, but the reason it's not an ice diagram is this is not an equilibrium problem. In other words, this reaction goes 100% to completion. This is a Gen Chem 1 limiting reactant problem. Remember, an equilibrium problem, we don't know how much reacts. That's what the Kc, the equilibrium constant, will tell us. In this reaction, we know how much reacts, 100% of the limiting reactant. So if we want to figure out what we have at various points along this reaction, we need to know how many moles of each of these things we have. Okay, again, at the equivalence point, we have equal moles. What about before the equivalence point? Well, before the equivalence point, we have not added enough of our base to react all of our acid. So in other words, before the equivalence point, our OH minus is going to be the limiting reactant. I'm just going to make some numbers up. Your numbers will be different for your calculations, but let's just make some numbers up. Let's say I start with 0.5 moles of HA. All right. Let's say I've added 0.25 moles of OH minus. So what the B means is before this reaction. And again, this is not a nice diagram. I'm not putting concentrations in here. This is just a way of organizing my limiting reactant, my Gen Chem 1 problem. So before this reaction, let's say we started with 0.5 mole of HA, and we've added 1/4 mole of OH minus. Well, which one's the limiting reactant? Because they react in a 1-to-1 mole ratio, the one you have the least moles of. So OH minus is my limiting reactant. This is before the equivalence point. Okay, this is the big difference between this and equilibrium. We know what the change is, right? We know how much reacts. All of the limiting reactant reacts. So how much OH minus reacts? All of it, 0.25. Well, how much HA reacts? They react in a 1-to-1 ratio. So if a quarter of a mole of OH minus reacts, a quarter of a mole of HA reacts. And what have we made? A quarter of a mole of A minus. Sweet. So before the equivalence point, what are we left with? We have some HA left over. And in this case, we have a quarter of a mole of HA left. We don't have any of our NaOH. It was the limiting reactant. It all reacted. And we have produced a quarter of a mole of A minus. So notice, before the equivalence point, we're going to be left with HA. And what else do we have floating around in the solution? We have also produced some amount of A minus. Okay, how would we find the pH of this solution? Well, notice, before the equivalence point, we have our weak acid left over and some amount of its conjugate base. In this solution, we have two important components, HA and A minus. And this type of solution, as you know from lecture, is called a buffer. A buffer is a solution in which we have a significant amount of a weak acid and its conjugate base both present. What is an important property of a buffer? Well, a buffer resists a change in pH. Okay. How would we find the pH of the solution in lecture? Well, this is a buffer. So we can just use our Henderson-Hasselbalch equation to find the pH. The pH equals the pKa plus the log of the base, which is A minus, over the acid, which is HA. Okay. Using these numbers, how would we find the pH? Well, notice at this specific point of the reaction, it's before the equivalence point, but let's be more specific. The equivalence point would be when we've added equal moles of these two. We haven't added equal moles. We've added half of the moles of OH minus at HA. This specific point of the reaction is at the 1/2 equivalence point. It's not the equivalence point. The equivalence point will be 0.5 and 0.5. We're at 1/2 of the equivalence point. We've added half of the amount of OH minus as we had at HA. So notice, what is true at the 1/2 equivalence point? At the 1/2 equivalence point, we're going to be left with a buffer where, no matter what these numbers are, if we're at the 1/2 equivalence point, we are left with a buffer that has equal amounts of HA and A minus. Going over to our Henderson-Hasselbalch equation, what would be the pH of the solution? Well, at the 1/2 equivalence point, you have equal amounts of these two. So this ratio will be 1. What's the log of 1? The log of 1 is 0. So what is true at the 1/2 equivalence point? At the 1/2 equivalence point, you are left with a buffer where this term goes away because A minus and HA are equal. At the 1/2 equivalence point, the pH equals the pKa of our weak acid. Okay, we need to use this idea to identify what the unknown acid is. Because if we measure a titration curve, we're going to figure out where the equivalence point is, so we know where the 1/2 equivalence point is, so we can find the pKa. If you know the pKa, you can look up values of pKa's of unknown acids, and you can identify, or at least have a good guess, as to what the unknown acid is. Okay, so let's get back to our titration curve, and what is this going to look like? Again, we're going to make a plot of pH versus milliliters of NaOH added. I'll rewrite the reaction. Okay, so before the equivalence point, the pH increases, and we're left with a buffer. And what do buffers do? Buffers resist a change in pH. So you will notice, as you add OH minus, the pH goes up, 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 but very slowly, because we have a buffer. It's resisting a change in pH. But at some point, we exceed our buffer capacity. We add enough OH minus to where we're no longer left with a buffer. And once we get rid of this buffer, what's going to happen to the pH? The pH is going to increase very rapidly. Then it starts to level off, but keeps going up over time. Okay, the steepest part of this curve, the steepest part of the curve, like right in the middle, right here, is going to be the equivalence point. The most dramatic change in pH occurs at the equivalence point. So if we measure this titration curve, we take all this data, we can figure out where this inflection point is, the steepest part of the curve. We can estimate it, right? So we can figure out where this equivalence point is. Well, let's say this equivalence point, I'm just going to make some numbers up. Let's say this equivalence point took 24.00 mils of NaOH. 24.00. How would we find the 1/2 equivalence point? If it took 24 mils to reach the equivalence point, it would take half of that, or 12.00 mils to reach the 1/2 equivalence point. Could we figure out the pH? Yes. Could we figure out the unknown acid then? Yes. Okay. How are we going to find the concentration of the unknown acid? Well, just like week 1, we're going to know where the equivalence point is. We know the concentration of NaOH. We know the volume of NaOH it took to reach the equivalence point. So if you know molarity and volume, you can find moles of NaOH. At the equivalence point, the moles of NaOH will equal the moles of our weak acid. So we know the volume. We know the molarity from week 1, so we can find the moles. We know then the moles of our weak acid, HA. How do you find the molarity of the weak acid? Well, once we know the moles of our weak acid, we can divide that by the volume of our weak acid. So you got to know what volume of weak acid was used. Once we divide by the liters of our weak acid we used, that'll be the concentration of our unknown acid. Okay, so what you have to do for this lab, you have 2 sets of data. I want you to plot these titration curves on Microsoft Excel and obviously turn them in with your lab report. Based off of these 2 titration curves, you should be able to find a concentration of unknown acid from each one. So you should be able to find an average concentration of HA. And you should be able to identify the unknown acid based off of pKa values. All right, that was a lot. I hope it makes sense. If not, email me and I'll help you out.